Good morning. All right. Hopefully you can hear me. The stream was having some connection issues earlier, so I think I've fixed it all out, and hopefully you can hear what I'm saying and see what I'm doing. It seems to be working on my end, so that's a good start. Today is not an easy topic, but we are going to do it the easy way first. And that's going to be having the computer do it for you. Tomorrow we're going to look at the same topic, only we're going to focus more on doing it ourselves to see what we can get. And we're going to do it that way so we can actually explain the math behind it and why we want to do things this way. In the real world, you're probably just going to get the computer to do it for you because everybody seems to have access to computers these days. So today we are going to be talking about modeling functions. What that means is, given a set of data, whether you did an experiment in science or something, you came up with a whole bunch of data points. You had your graph, you had your independent variable x values, you had your y values, you plotted a bunch of points. Doing it, you then want to look at that data and see which type of function is modeled best by it, and then find out what the equation for that data is so you can then make predictions based off of that data, and apply it to other scenarios. You only take a sample group when you do scientific research and stuff. You don't test every single person in the world. So you only test a sample, and then you want to see how well does that sample fit the rest of the world. That's important information, because if you're only taking a sample of, I don't know, for your science projects, people in at least the Pittsburgh area, is that actually true for people outside the Pittsburgh area? Well, you put it to a model and you test that model. So this is actually extremely important when it comes to scientific research and stuff like that. And there are other types of models as well. We made a little booklet of all your different function models. I mean, you have absolute value models here, so maybe it fits an absolute value model better. Maybe it has a logarithmic model that fits it better. The three that we mostly focused on this year were linear models, which we did at the very beginning. Then we went to exponential models, and then we went to quadratic models, which we just kind of are finishing up. There are other types of models as well. There are multiple degree polynomials, right? Each one of those is going to have a different model to it. So if you wanted a third degree polynomial, fit to that. You have trigonometry functions. Maybe it follows a trig pattern like a sine curve or a cosine curve or a tangent curve, things like that. But the ones that we focused on were linear, quadratic, and exponential. And I'm going to just review with you real quick what those look like. Hopefully you remember our forms of each. This, again, is not standard form, but it is probably the form that you see the most. So this is kind of the easiest form to use when it comes to writing models for lines, which is slope-intercept form. Remember that m is your slope and b is your y-intercept. And coming from a graph, if you're looking at a graph of a line, you can pull that equation out pretty easily, looking at the y-intercept and calculating the slope with 2 points, or using rise over run. But hopefully I don't have to remind you that a linear graph, and we're going to do linear in blue here, so I'm going to underline that in blue. Linear is going to be blue. Linear is going to be a simple line. So let's get our ruler out here, and I will just model a line with you. Hey, this here is what a linear function is going to look like. I'm not in that layer. Well, did that work? That did not work. Move that up. There it goes. There's my line. Right? So this is just your line for your linear function. Remember that does have arrows because it goes on indefinite. That's what a linear function looks like. It looks like a line. Looking at our quadratic function, let's put our quadratic over here. We'll do quadratic in red so you can match that up if you're viewing it. Remember, our quadratic function has that axis of symmetry to it, and may or may not cross, well, I didn't get rid of that, may or may not cross the y-intercept, but it looks like a parabola. It has that shape. Keeping in mind that higher degree functions of your quadratics, like quadratics are only a second degree, but when you get to your higher degree, like a third degree function, it's going to just turn that parabola back down on a way. It'll look like that, maybe. But we're not concerned about that today. We're looking at just the parabolas. So you have linear functions which make lines, quadratic functions which make parabolas, and then if you recall your exponential functions, it's probably been a while since we did exponential functions, but let's do exponential in green here. Exponential functions are going to look something like this. And this is that curve you see in the news all the time about the coronavirus, because it is following an exponential model. Scientists took the growth of that virus and applied it to an exponential model to get that graph. And then with that graph, we can have projected amounts from it. And then we can do studies and see, okay, how is social distancing actually affecting it? We can take a group, we can study them, and right now we're not really sure because we don't really have much of a control group to compare them to, due to the fact that everybody is being asked to social distance. And we can see how that curve is going to change, whether it's going to flatten out, which is what we want it to do, and eventually we want it to stop growing and we want it to decrease, and whether is that going to decrease in a linear fashion, or is that going to decrease in an exponential fashion, or is that going to decrease in a logarithmic fashion. And then they're going to fit a model to that so they can predict things. And it's actually pretty important when it comes to scientific research and showing if things actually have relations to each other. So fitting these to models is what we're going to do. So our goal today is we are going to be given a set of data. We're just going to be given some points. What do I want to do here? Let's get rid of all of this. We're going to be given a data set. So here I went ahead and just copied number 1 from your homework. So we are looking at this data set right here. We're given a set of data. So if you could imagine you did an experiment and you came up with all these were your inputs, right? Those were all the times you tested, maybe, I don't know, and this here was your output. Your inputs are your independent variable and your outputs are your dependent variable. And what you want to do is you want to graph this and find a model that fits this. So what we're going to do is we're going to do this the easy way. So first we want to, let's change my color back here. So first we want to graph it. Then we want to decide what model fits best. And again, our options for this are, is it a linear model? Does this data fit a line? Is it a quadratic? Does this data fit a parabola shape? Or is it an exponential? Does it fit that other shape I showed you, that It goes like that, right? So which one does this data set represent? In all honesty, it could represent all of these. I mean, we could make a model that represents each one of these, and we're actually going to do that today. We're going to take number one, we're going to make a linear model that suggests it. We're going to make a quadratic model and an exponential model. Yeah, Ed, I'm sorry about that. We're on this page right here. I thought I changed it in time, but if it didn't take on yours, do it on yours. I'm actually going to do number one with you and hopefully get you through a couple of these today. We are going to be doing the same thing tomorrow, just we might be doing it differently, and depending on how far we get today, because there's a lot I want to explain to you today. And I hope you understand the importance of this. This is where like the meat and potatoes of algebra is coming into play. How do we explain things that are going around, and how can we make predictions about the future with it? And again, that information is extremely valuable to scientists in the world of especially medicine right now. But it can help with curing other diseases as well. Mental health issues can go with this. Population studies go with this. I mean, any type of scientific study is going to use this information. And it's going to be beneficial for you to know how to do it if you want to actually be able to read a study, or even when you get older, do your own. But here, these are the things that we want to actually accomplish. We want to be able to graph our data. We want to be able to tell what kind of data it fits. And we want to be able to find the equation to represent our data, right? This here is your raw data. This is what you actually went out and experimented with. Can you graph that? Most of you probably can, because you had to do it for science, right? Can you find a model that fits it? Some of you, actually all of you have done this before. We just didn't. We just only did it with linear. So that part should be kind of a review for you. If you remember when we did scatter plots a while back, but we're going to add quadratic and exponential to it. And then once you get that graph, can you look at that graph and make the equation? Again, linear you probably can. Exponential and quadratic you might still be a bit rusty on, especially quadratic because we haven't done it yet. But we're going to look at this data set and we're going to do it. And today we're actually going to do it through Google Sheets. So we're going to actually pull up Google Sheets. So today we do it through Google Sheets. We're going to use Google Sheets. And tomorrow we're going to do it by hand, which is going to obviously be a little more difficult. Google Sheets is going to do most of the math for you. And that way you can actually understand what's happening and how different things look, and it'll be easier to compare them, so you can see which one's going to be a better fit. So what I'm going to ask you to do is to pull up a Google Sheets. I have one pulled up here, and before I show you mine, I'm just going to transfer this data into Google Sheets so I don't have to keep switching between my windows. So actually, I'll move this window over here. See how well this will work. Here's my Google Sheets. I just named it Modeling Practice. I'm going to make an XY table here. So in cell A1, I'm going to put X for my X values. In cell B1, I'm going to put Y for my Y values. And underneath, I'm just going to fill in my X values. It does not matter the order you put them in, as long as your X value is matching with your Y value, that's appropriate. So if you recall the problem, the first X value I had was -2. So over here I'm going to write -2. And its Y value for it was -3. And I'm going to just fill in all my points like such, making that XY table out of it that we've done so many times already. 1 and 0, 2, and -3. So if you should be following along if you have the ability to do so right now. If not, then make sure you rewatch this and follow along when you can. But this is problem number 1. And again, what we want to do is we want to be able to graph this. That is our first goal, is to graph this. So what we're going to do is we're going to highlight it and go to Insert, Chart. And our chart, we do not want a line chart. We want a scatter plot. Scatter plot. And so under setup, change it to scatter plot, just like that. And then over in customize, just so you get a better view of this, you're going to click on your horizontal axis, which is your left and right, and we're going to change our min and max down here. So just scroll down to your min and max. We're going to make this -10, and we're going to make this +10, just so we get, hey, this goes all the way out to 10s on those sides. And then you're going to do the same for your vertical axis. Scroll down to your min, make that -10, and your max, make that 10. So it's just going to count to those. And then you get a look at it, and right away you should be thinking, hey, is this linear? Is this quadratic? Is this exponential? And just looking at it should give that away most of the time. However, not always, because depending on what data you put in here, you might not actually see the curve of this parabola. You might get something else. Your book is probably not going to give you anything strange like that, but you don't know. So what we're going to do next is over under the Series tab in Customize. If you recall, we did this a while ago. We're going to add a trend line to it. And we're going to click trend line. And this trend line is going to predict the data. It's going to say, okay, what line best fits this data set? And the problem with that is it's going to look like this. And your trend line is right here, which does not fit that data very well. Well, if you continue scrolling down, you'll note that this is fitting it to a linear model. It says right here, this is a linear model for it. And right now we're actually going to keep it as a linear model so we can talk about linear models. But this here is a linear model. The next thing you want to know is this model a good fit for this graph? And just by looking at it, you're probably thinking, Mr. Brandt, that clearly isn't. But due to the fact that you don't know, you can't just take based on, hey, what does it look like? You got to have the math and the numbers to back up your opinion. You can't just say, well, I think this is a linear model. Well, why do you think it's a linear model? You need to be able to support that. Science is all about finding the evidence that supports it. So here, if this is a linear model, which we could use a linear model to do this, we're going to come down to this little checkbox here that says show R squared. And R squared is a regression coefficient. We're going to click it, and it's going to come up, and it's going to say up here R squared equals 0. That is our regression coefficient. When it comes to regression coefficients, and I'm going to bring my sketchbook back up in a second here so I can write this. Let's get a new one though. So when it comes to regression coefficients, so when you have R squared, which you're not going to be asked to find, you're going to have the computer find it for you. R squared is your regression coefficient. How do you spell that? I think there's a C in there somewhere. I don't know. It's your regression coefficient. This is going to tell you how well does your data fit your model. In your regression coefficient, if you remember, we didn't find regression coefficients before. We found correlation coefficients. I had you type in the function like equals correl, parentheses, and then you had your groups, and it gave you a number between -1 and +1, and you got a number between those two. right? That was your correlation coefficient. Your regression coefficient, and believe it or not, this correlation coefficient actually equals R. So your regression coefficient is taking your correlation coefficient and squaring it, and you're going to get your regression coefficient. Your regression coefficient, because it's squared, means it has to be a positive number. So you can take whatever this is, square it, make it a positive number, and R squared you can think of as a percentage. So, but it's going to give you as a decimal. R squared you can think of as a percentage. The higher the percentage, the higher R squared is, the better it fits. So here, in our linear model, R squared is 0, meaning that is 0%. So for our linear model here, 0%, R squared equals 0%, it does not fit that model very well at all. And that's pretty obvious just by looking at it too. So now you have actual data to sit there and say, hey, this is not a linear equation. This linear equation has a regression coefficient of 0, meaning it doesn't fit the data. So we don't want a linear equation. So linear is out. We're going to throw that out. This is not a linear function. So we're going to come over back to our customization. I think we're in series still. Yeah, we're under series still. And you're going to change this from linear to another one. And look, you got all these different options. Let's go to exponential next because it's next on the list, and we know it's not exponential just by looking at it. But let's put it as exponential. And we're going to add a trend line for that as well. And you can see that the exponential trend line is looking very similar. Let's see, did it work? Yeah, because it's not really an exponential function. So it's not going to look anything like what an exponential function should look like. I mean, it's trying to go up, but all my data is going down from now on, so it's not going to fit it. So again, you get an R squared value of 0. However, if we go over to polynomial, and we change, and this here's your degree of polynomial, so that we want to keep this as a 2, but just so you know, you can do like third degree polynomials or whatnot. And our R squared condition now goes to a 1, which is a perfect fit. And due to the fact that this is math and your book is just introducing these to you, you're probably going to get perfect fits. However, when you do actual experiments, there's going to be so many confounding variables thrown into your design probably that you're not going to get a perfect fit, and you're going to ask for a confidence interval, and you're going to be like, well, if it is like 95% good, it's going to work, just because there's so many different things that could go differently during each individual experiment. So in this case, our R squared coefficient, or our regression coefficient, is 1. That's what we want to see. We want to see something that is a high percentage. And again, that is as a percent. So that's 1 written as a decimal. Make it a percent, that's 100%. So here, our regression coefficient fits. It supports our decision saying, hey, I want this to be a quadratic. So I think I deleted my sketchbook. But let's go back to where I can write. And what we're looking at is number 1. I'm not going to recopy the data. This is page 563. Number 1, it fits a quadratic model. So the model that it fits is, that's not how you spell model. I don't know, is a quadratic. And again, you know that because of your R squared term, but you also know that by looking at it, just kind of eyeballing it, and seeing how it makes that design. So that does fit a quadratic model. And I think that's all it's asking you to do for 1 through 6, is to find that quadratic model. However, we want to actually find the equation too. So let's look on how Google Sheets here will find your equation. right? So we know it's going to fit the equation y equals ax squared plus bx plus c. And Google Sheets does it a little strangely. No, Audrey, it's page 563. I think 559 is where the chapter starts. The problems you're doing are 563. I thought I changed it in time, but it might not have taken to everybody's. So I apologize for that. But we are looking at 563. So the equation has to fit this a squared plus b, or ax squared plus bx plus c, because that's our quadratic equation. So let's go back to our Google Sheets, wherever it landed. Boom, there it is. And let's get the equation from it. That's all right, Audrey. What we're going to do is we're actually going to have Google Sheets tell us the equation. That's going to come down to this label thing. So you can see where it says label here. What I can do is I'm actually going to deselect r squared because it's going to stick it up here with the label. So it's labeling it with r squared here. It's calling it the trend line. I'll do it both ways. But if you click here, you get the option of none, custom, or use equation. Well, if you click use equation, it actually puts the equation right there for you. It tells you y equals 1 plus 0x plus negative 1x to the second. Just keep in mind that's not written in standard form, because in standard form we want the highest degree monomial first. So when we go to write the equation, just make sure you write it in the other way of doing it, and also clean it up, because we don't write negative 1x squared. We just write negative x squared. We don't write 0 times x. We just leave it off. And then your C term will be the 1. So just be careful on how you read it, because it is going to give it to you, 1, the way that the computer types it, as opposed to the way that the mathematician handwrites it. And 2, it's not going to be in standard form. So you're going to have to mess around with that a bit to get it in standard form. But we can come over here and we can, this is going to disappear anyways. You can't see it, but I can still see it. In our equation, I'm just copying it from that other thing in standard form. Well, let's copy it first. It gave it to you like 1 plus 0x plus negative 1x to the second. It gave it to you like that, but you can clean that up. You know this is not necessary. 0 times x is just 0. And you know that we don't write that 1 in front of that, and we don't write exponents like that. So it's going to be negative x squared plus 1 equals y. And that is the equation to model that situation. In this case, that's going to be the exact equation for this data set, because it's the math book and that's what it does. But in real life, it's going to be the model of it, because you're not going to have exact numbers for your experiment. It's just going to go off and be a little different. And honestly, once you get this set up, it's pretty easy to just go and change them. So looking at number 2, and if you want to look at number 2 in your book, we can just go ahead, delete our x values and y values, and type in problem 2. Problem 2 says, just going across our x values, we got negative 2 goes with negative 8 for the y. So our first point is negative 2, negative 8. You get 0 and negative 4. You get 3 and 2. You get 5 and 6. And you can see right now it is trying its hardest to put this to a quadratic, and it's getting pretty close to it, but you don't see the data going elsewhere. So this could actually be a quadratic. It's probably not your best choice, but your r squared value is going that way. Another reason why it's important to collect more data. In this experiment, they only had a sample space of 4. Right? 1, 2, 3, 4. Yeah, it only had a sample of 4. That's not enough data to make any real decision off of. You can't just go around and ask 4 people what they think and their opinion and then base everything off of what those 4 people said. It doesn't work too well that way. But you can go back into your customize, you can go back into your series, you can go back and look at how well each of these fit. Exponential, not going to fit too much. You see how it's trying to make that curve going up. It does fit some though. However, this data doesn't fit well. Linear is going to fit really well because this looks like a linear equation. However, you can sit there and with the information given, because the computer program is trying really hard and it knows that this is possible to fit into a quadratic. It is possible to have this part of a quadratic equation. I mean, you can just imagine how thin that line would be, how steep it would be, and eventually over here it's going to curve around. I'm not sure if we can go ahead and increase that to see it. Let's change our horizontal axis, our min and max. We're going to play with our min and max. Let's take it out to 1,000 and see what that's going to look like. And then with our y value, this might work, it might not. Take that out to 1,000 as well. And it's still looking like it doesn't want to curve just yet. But eventually it's going to think to curve off, and it's going to be a whiles out there because these numbers are trying to get close to it. But it does fit the linear equation better. And again, you can sit there and you can eyeball that, but you could also sit there and make an argument that this is a quadratic. It's just a linear is probably a better choice. Let's change the x values back. Right. So this does fit a linear equation. Again, it does give, well, that's the quadratic version. And series, and we can go down here and say show a linear equation for it. And this here is the linear equation for it, 2 times x plus -4. So this is 2x plus, or 2x minus 4 is your linear equation for it. So for number 2, you're going to write linear. And I know you're probably going to hate me because we were trying to figure out equations of these lines way back then, and I didn't tell you could just click over here to get the answer. I had you actually figure those out by hand. So now you know that you can just click there and get the answer. But it does fit a linear pattern pretty well, so we are going to call that linear. So on your work, you pretty much, for number 2, it's going to be a linear model. And model is EL, isn't it? There's my horrible spelling coming into play. It is a linear model, and again, you know the equation because it gives you the equation was what, 2x minus 4. I'm just double checking that. Yeah, 2x minus 4, and does that. So what you can do is you can go ahead and finish off 1 through 6 here just by changing these values here. So we're going to go ahead and change them to number 3. And let's look at what number 3 looks like. See if we can get an exponential one. We haven't had that yet. Number 3 says -3 goes with 6. -1 goes with 0. 0 goes with -1. And 1 goes with -1.5. So there's that. This one here is looking more exponential. You can see our R factor here is trying to get it linear, but it's not going to fit perfectly. That is at a 89.9% though. So that is actually a fairly decent regression, depending on how confident you want your data to be. It's not the worst model for it, but let's see if we can find a better one. So again, we're going to go to edit chart, going to go to series, we're going to look for a trend line that is exponential. It might not like that. And let's try polynomial. That's a little better fit. It's not exact. This does look more like an exponential one, but it is kind of like the negative version of the exponentials. So let me double check what the book is actually saying this is. And it's all the way in the back. Yeah, your book does want this to be exponential. I got to play around with Excel to figure out how to do the, or I'm sorry, Google Sheets to get the exponential curve going that way. I'm not sure if it likes that. I think a power series is going to be it. So I'm not sure how well that's going to fit. I mean, the quadratic does fit pretty closely too, but exponential does look like it's going more. And it's really hard when you only have 4 points of data to assign something as well. So you can sit there and argue exponential too, but getting the equation for that's going to be tough because it doesn't want to show me that. Let's see. Yeah, I'm not finding situations to show that. I might look into that and come back to you tomorrow with some, but it does look better as an exponential function, just kind of the way it looks. You can sit there and argue that it is a quadratic because that quadratic did fit pretty closely. It's 99.8% accurate on there. I mean, that's not 100 like your book is looking for. Trying to get the linear one or the exponential one. Let's make sure I copied everything right. -3 and 6, 1 and 0, 0, -1, 1 and -1.5. Yeah. So I'm not sure what's going on with the exponential one there. I don't know if one of the other ones will or not, but you can see that it's possible that this might be a quadratic relation as well, just because we don't have enough data to see if it's going to go back up here or not. Very well could. I don't know why it's not doing the exponential one right now. I have a feeling because the exponential one wants to go this way, and this doesn't fit that at all if it's going this way. And I'm not sure how to tell it to do the negative exponential. I might look into it and let you know tomorrow. But go through, see if you can, and again, it's not asking you for the equation for 1 through 6, it's just asking you what model best fits it. So go through with Excel or Google Sheets, see if you can come up with a best fit model for 1 through 6. We'll go over this more tomorrow. We'll start doing it by hand some, and maybe even into Friday because it does get a little complicated. But in all honesty, this is the way you're going to do it in real life. You're going to get a computer to do it for you. It's just going to be more accurate and precise. I mean, look at, I mean, if this was a polynomial function, look at the equation for that. You're not going to find that by hand nicely. I mean, you can. It's just, that's going to be annoying. And it is a pretty good fit. I mean, it's 99.8%. So, with that, give it a shot for the next 3. And again, all that you're doing is in the space writing linear, quadratic, or exponential in the space next to the number. That's all it's asking you to do, which model fits it best. Tomorrow we'll look at getting the equation by hand and going from there. So I am going to end it. Good luck with everything. email me if you have any questions about anything. Talk to you later. Bye.